So last time we were talking about operator norms, and I think we are done now with that. Was one step where I kind of blanked out. Then I went back to it later. I don't know if you've looked at it, and I think it just makes sense. Where was it? Yeah, this inequality here, that the Frobenius norm of A transpose A is less than the square of the Frobenius norm of A. And if you think about it, the singular values here are the squares of the singular values here. Right? So you're saying that the sum of the fourth powers of the singular value square rooted is less than the sum of the square of the singular value. That's pretty clear, right? You can write on this. Maybe let me right here on the new lecture. So basically, we're saying that the square root of that, sigma r, is less than the square, which eliminates the square root of the, of the sum of the squares. And to see that, just square both sides, then you eliminate the square root. And but on this side, when you square, you don't only square the the diagonal terms, which become fourths, but then you have all the other cross terms. So that makes sense.
Yeah.
All right. So let's start on chapter 2 now from the book, which talks about perturbing linear systems. Again, we're going to have to review a little bit of matrix theory. So in matrix theory, we often set up a system of equations in this general form, ax equals b, and then you want to solve for x. Right? That's the typical, the most general linear system of linear equations in several unknowns. So A and B are given. Those are the data of your problem. And then, you're trying to find X, the solution. So, and let's assume here for simplicity that that A is invertible. And we know in that case there exists a unique solution. This in math, exist unique, we write like that. Backward E with a exclamation point. So far, so good.
Mhm.
All right. So from the point of view of perturbation or uncertainty, right? There should be, so if there's some uncertainty in the data, then there's going to be some uncertainty in the solution. Right? So that's kind of the way you want to see this. Almost think of it as a function, right? That given A and B as input, spits out X as an output. So that's the function that we'd like to perturb. And so one way to do that is to say, okay, so if we don't know A exactly, then we are actually dealing with A plus a little small error. If we don't know X exactly, then we're dealing with X delta X, and that might equal B plus delta. So that's the most general way of thinking about this. And and here X is the exact solution, right, from up here. So for instance, if I distribute this, then AX, A delta X, and then delta AX, delta A, delta E, E. Because X is the exact solution, I can actually cross out those two terms. And now I can maybe collect some things here. Let me collect those two. So A plus delta A applied to delta X equal delta B minus delta A. Let's assume again that because A was invertible, the perturbed version is also invertible. And we'll see more specific instances of that later. So we can invert here, we can multiply by the inverse. And we get our forward error, right? This delta X would be the forward error. All right, questions so far? Well, let me tell you a little bit more about this inverse here. So one way to rewrite that is to take out A from this expression, right? So I take out A and write it like this. Then when you do the inverse of a product, it's the product of the inverses, but in the reverse order, right? So you're gonna write this write it like that. And now we can go ahead and take norms. In all of this, now we know that we have a wide variety of norms that we can choose. If I don't say anything, usually I'm thinking of the two norm, and the induced operator 2 norm. But I think in this case, you'll see what properties of norms we actually would like. So for instance, if I take the norm here of this, then it would be nice to have the submultiplicative property, right? As long somebody said something. Question about delta.
I well, first excuse the background noise, but delta is a scalar, correct? And if it's a scalar, then why would we? When we had delta times a delta, why wouldn't we say delta squared is too small and get rid of it? Is there something about the term we'd want to keep it, that delta A, delta X?
So delta is not a scalar here.
Okay.
But you're not, yeah, but you have a point. So delta here is just notation. Delta A is one thing. It's just that's how we call the perturbation of A, the little error. Delta X is
Okay.
It's just a word, right? So
yeah. Okay.
It doesn't actually mean delta times X. But you're right that here, when you have delta A, delta X, right, you're compounding two small things. This should be really, really small, and we probably don't need to worry about it. Is that what you were saying?
Yeah, I was wondering why we would need to worry about it, if maybe it had some significance or.
Yeah, no, you're right. In general, this is going to be a higher order error, and then it's not really going to matter as much. But there's several approaches to this. The book takes does it in two ways, and this is the first one. Let's continue here for a second. So I'm going to take the norm of this expression here, and I'm going to use the submultiplicative property. So it's going to be less than the norm of this inverse norm of that inverse, and then just the norm of that vector. And then if I use the triangle inequality, and I want to think of this as some kind of a constant here. Here we are perturbing the identity by a little bit and taking the inverse and a norm. So this should not be too bad of a constant. What matters here is this norm of the inverse. And then, so this is going to be, if I use the triangle inequality, this is the submultiplicative property. S and P. I'll use that notation. Triangle inequality. So what do we get? We get the norm of A inverse. And then here, I can separate it out of the sum of the norms. And then I can even use the submultiplicative property again. Well, no, this is just it's one of the property of the operator norms. So Yeah, so let's assume here that this is an operator norm. And if we do that, either an operator norm or a Frobenius norm. Frobenius norm. Then all of these things are okay to do, right? From what we've learned last time. Is that good here? All right. So let's divide now to get the relative error. Um, get that. So this is the relative, in a sense, forward error. And then and here I'm going to take out, actually, I'm going to do a little bit of cosmetic rearrangement. I'm going to take out the norm of A. And write it like that. And the reason is because, okay, so here I have a relative error in X, and it's bounded by the relative error in A. And this term here, actually, again, by the property of operator norms, right, since B is AX, right, then norm B is norm AX, which is less than norm A times norm X. Right, so this here, this denominator is greater than norm B. I'm dividing by something bigger than norm B. So if I replace it by norm B, then I get a bigger fraction, right? So norm B, delta B over norm B plus delta A. So that's kind of relating the forward error to the backward error in a sense. And so in relative terms. And so this is just a constant, right? Because it's kind of a universal constant type thing. So really what matters is this product here. And this product has a name. It's called the condition number of the matrix. Usually denoted with a kappa. And it's just the product of norm A times norm A inverse. Questions? Good?
Mm-hmm.
All right. Let me go a little bit into more details about some of the passages here. In particular, the fact that this is a constant, right? So let's think about this a little bit more detail. I'm going to have to review a few technical things. So here's a lemma. Let's assume that you have a norm on the square matrices, and it's a submultiplicative. Right, like an operator norm or the Frobenius norm. Then if you have a matrix X of norm strictly less than 1, then if you perturb the identity by X, you still are invertible. Right, so the identity is obviously an invertible matrix. If you perturb it by something small in the norm, you stay invertible, and the norm of the inverse is less than 1 over 1 minus the norm of X. And so I'm going to refer to this as the Voigt-Neumann result. This is a famous mathematician, von Neumann, is related to this type of result. But essentially, it's a generalization of the geometric series in calculus. So let's review that a little bit. I so recall if little x is a real number, a real number, then if you write 1 plus x squared plus x cubed plus xn, right? Geometric series up to n, and you multiply this whole thing by 1 minus x. Okay, so what happens when you distribute the 1? You end up just copying the sum, and then when you distribute the negative x times 1, negative x times x, all the way to the last one is negative x times x to the n, so that's negative x to the n plus 1. All right, and so when you sum this, they cancel out. All these things cancel out, and you're left with that term, right? So it's called telescoping. So, all right. So that means that the sum of x to the k goes from 0 to n. 0 because, 1 here is x to the 0, and x is x to the 1, etc. We're thinking k equal to 0 gives you the 1, k equal to 1 gives you the x, k equal to 2 gives you the x squared, etc. This sum is 1 minus x n plus 1 over 1 minus x. And this is an identity. This is true for any real number. But the question is, what happens if I let n go to infinity? Right? And so here is where you might introduce a condition, and you can say if the absolute value of x is strictly less than 1, well, then x to the n plus 1 goes to 0. And so you can take the limit here, and you get that the total series from 0 to infinity converges to, the limit as n goes to infinity here is 1 over 1. This is a very famous formula, very useful in many, many situations. So, well, now let's think about X as being a matrix, an n by n matrix. So what does it mean to have a geometric series in this case? This identity that we proved up here only depended on the rules of arithmetic, when you distribute a sum, right, with the product. And there's no issues about commuting because these are powers of a single matrix. So this is always true. So the same proof shows that if you take the identity minus x and you multiply it by the identity plus x squared plus x to the n, you get identity minus x to the n. I'm going to use capital N here because I have little n there. Right? That makes sense. This is just an identity for matrices that I can just see by distributing and canceling. All right. Now it's a little bit harder with numbers. We just divide it by 1 minus x, right? But we can't really divide by a matrix by another matrix here. Only if this thing was invertible, we could then take the inverse of both sides, and then, but we don't know that I minus x is invertible. This is part of the conclusion of the lemma, what we want to prove. All right, so let's try to prove that. So first, note remember when we study norms, because of finite dimensionality, all norms are equivalent, right? So that's something we mentioned before. So whatever our norm is for x, there's going to be a constant c, so that our norm is equivalent to the max norm. And so the max norm is the maximum of the entries for all INJs. This is certainly going to be less than a constant times our given norm that we started with. So remember, we start out with a norm on matrices, and the only thing we want of that norm is that it be submultiplicative. That's the only thing we want to ask of it. And the first thing we do is we say, okay, without loss of generality, we can talk about the max norm. Because there is this universal constant C, which will depend on our norm. It's universal. Well, it's not universal then. Okay, so it's a constant C that depends on our norm. But it's once you fix a norm, C is fixed as well. That's what I'm trying to say. And so then for every integer k, let's take the maximum of the kth power of x. Right, so I'm looking at kind of like here, right? When I'm trying to show that the powers of x go to 0. So I take the kth power of x and I look at its largest entry. And by this observation up here, so I see what the problem is. This inequality here holds no matter what matrix X you use, not just the one you. So maybe I should call it A here. Well, I think it'd be less confusing if I use A here. This is true for every A. Right? So I can apply this with the same constant C to any power of X. And get that. Does that make sense? All right. But now let's use the submultiplicative property. The norm of a power is the power of the norms, bounded above by the power of the norms, right? But by assumption, this is a number now less than 1, and so that tends to 0 as k goes to infinity. That make sense? All right. So how many people here have had advanced calculus?
Last fall, just in wonder.
Sorry?
I had it last fall, just the first semester.
I've taken advanced calc 1 and 2.
All right. So you're familiar with the notion of a Cauchy sequence?
Yes.
All right. So basically, I want to show that the entries, so I'm going to let's call this Sn. Sum k goes from 0 to n. Okay, right. I want to show that the entries of Sn of this partial geometric series, partial sum of the geometric series, that the entries converge as n goes to infinity. That's the claim. And one way to show that a sequence of numbers converges is to show that it's a Cauchy sequence. Right, so let's fix some two numbers. Oh, I shouldn't use little m again. P maybe, P and M. So two numbers P and M, one less than another, and also fix I and J. These are just rows or columns. And let's form the difference where I take the ij entry of Sm, the ij entry of Sp, these partial sums, and I look at the difference. If I can show that this difference goes to 0 as P and M go to infinity, then I've proven that this is a Cauchy sequence, right? So, all right. So remember, these are partial sums. So I actually can write it in sigma notation. This is the sum from 0 to M, and this is the sum from 0 to P. So there's a lot of cancellation, and I can start at P plus 1 and go to M, and then take xk ij, right? By the nature of, partial sums. Now, using the triangle inequality, I can pass these absolute values inside. And then using this fact up here that the maximum entry for xk is bounded by this constant c times the norm to the kth power, this is going to be less than that. Okay. But this now, remember, our hypothesis is that norm x is strictly less than 1. This is a regular geometric series for real numbers, which we know converges because this is less than 1. And if a series converges, if something, a sequence converges, and then it is Cauchy as well, right? So that this means that this goes to 0. So we showed that these Cauchy increments, I guess they're called, I don't know, tend to 0. So sequence Smij a sequence which would therefore converges to something which we're going to call Sij. All right, everything on board with this?
Yep.
Cool. All right, so we have a limit of the partial sums. And it's a limit, it's like, it's a pointwise limit, right? In each coordinate, these things are converging. And so in particular, so we have Sm tends to S, and also we had that Xn was going to the zero matrix, right? Same argument. So we can take our identity, which was I minus X times Sn was equal to I minus Xn plus 1. You can take that identity and just let n go to infinity. And we're going to get I minus XS. Right, so this limiting thing, S, is the inverse of I minus X. Remember, I don't know if you saw this in matrix theory, but for square matrices, it's enough, well, only square matrices can be invertible, but also it's enough to check one, the left inverse property or the right inverse property. All right, so questions. So, the famous result of von Neumann. Sometimes this is called a von Neumann series. But in any case, we can go a little step further and then compute the norm, right? So also, the inverse S, so basically the series from 0 to infinity, and the norm is the norm of S, right? Which is going to be less than by the multiplicative, some multiplicative property is going to be less than the series of the norms. The series of the norms we know tends to this one. So we do get everything that was claimed in the lemma. All right, so how do we apply this back to what we were doing earlier? So earlier, I was looking at the norm of identity minus or plus A inverse delta A. Let me just go check if it was a plus. It was a plus. plus A inverse delta A. Okay, so looking at that, and from the lemma, then we can deduce that this is less than that norm, as long as that norm is less than 1. Strictly, and it's important that this be a strict inequality. Now, because we're thinking of perturbing A, delta A, you know, it's not difficult to believe that this can be achieved. Let me rewrite this. So I claim that I can actually use the submultiplicative property here. And kind of separate out the inverse and the perturbation. So the way I like to think about this when I do this kind of estimates is if I have a quantity that's in the denominator, the estimate will go in the opposite direction, right? If I have a negative, then the estimate will go in the opposite direction. But if I have something that's in the denominator with a negative sign in front, then the estimate goes in the regular direction, right? So if you didn't have 1 minus, you know, if you didn't have anything here, you just had this norm, then the submultiplicative property would tell you that this is less than the product of the norms, right? And but you know, it's in this more difficult function, but the order of the inequality is unchanged. All right, and so now if I make norm A appear here and use the condition number kappa, then I can write it like this. So really what I want is the backward error to be strictly less than 1/5. Which makes sense when the condition number is large, 1/kappa is small, and so I'm not allowed to perturb by much if I still want to get an inverse here. And I ran out of time, so let me stop here. But before we go, if you have any questions or any comments, let me know. Everything good?
No, thank you, sir. I appreciate it. That was a good lecture.
Okay, thanks. All right, I'll see you on Monday then.
That's good. Take care.